My name is Kevin Evans. I'm a professor of geology at Missouri State University in the Department of Geography, Geology, and Planning. In this presentation, Dr. Pavlovsky has asked me to present a little bit of information for the geography of the Ozarks and give you a little bit of background on what the geology is in the Ozarks as well. I'm going to go in pretty much through the entirety of Missouri, however, so we'll drift a little bit farther north towards the end of this presentation. But there's a common misconception, I guess I would start with, is that geologists study rocks, but we don't really study rocks. We study the history that's recorded in those rocks. At least most of us do. And so we're really folks who study time, geologic time. And in fact, when we talk about time, oftentimes this is called deep time. And so deep time refers to pretty much everything beyond human memory, all of that prehistory. And so it's written in the rocks, that history. And so when we study time, well, okay, I use this as a metaphor here for Salvador Dali's persistence of memory, but you can see the clocks all over this, image right here. But at the same time, it's like, what do we know and how can we learn? And in fact, I would argue that the rocks in the far background of this painting, in fact, are also a clock of sorts, if you will. And maybe not so distorted as the clocks that are around Salvador Dali himself here. When we look into the past, there's one way to do this easily is to get a telescope. And telescopes, when you point it out to the far distant stars and the galaxies, that's light that had burned light years ago. Okay, so the speed of light's pretty fast. And so when we train our eyes into the most distant parts of the geologic past, we can actually look into the universe. And so when you look back in the universe as far as you can go, and they did this with the Hubble telescope a lot of years ago, maybe 20 years ago, something like that. And they looked back and they trained at the darkest part of the sky that they could look at. And what they saw was it was totally populated with galaxies. So these are not photoshopped in this image. What you can actually see here is a clusters. People have estimated that there's 200 billion galaxies in our universe. And so that, all was a result of the Big Bang 13.7 billion years ago. And so, boom, all of a sudden you have this huge manifestation of matter and energy all within our universe, and it is expanding even more rapidly now. It's accelerating. And so we haven't begun to see the extent of what the universe could be. But when we look back, we can look back roughly about 11 billion years. Now, ironically, that is not the same age as the Earth, okay? So the Earth, in fact, is only 4.56 billion years old. And so with that in mind, we are actually made out of recycled stardust, of galaxies that have collided with other galaxies and, with stars that have been around for generations. And so in order to get the sort of heavy elements that we have on Earth, in fact, we have to have been recycled star material. And our sun is not the first generation star. It's made out of older star material and dust and gases that came together and accreted about 4.56 billion years ago. So that is kind of like a brief, where did the beginning of everything kind of come from? There's a famous geologist. His name was James Hutton. He's regarded as the father of geology, at least modern geology. And so he said that there's no vestige of a beginning and no prospect of an end. And he's probably wrong in both aspects, actually, because we know that the Earth began 4.56 billion years ago. And we know that eventually it's going to come to an end of some sort, when Earth is swallowed up by the sun. When the sun goes into a red giant phase, if it does that. And so we often think if the expanse is large enough that it goes on forever, but it's really not the case. Okay, so there is a timeline and a limited life expectancy for everything. And so I like to point out to people is like, you may think you own it, but you only rent it. You only rent it. It's only here for a short period of time. So here are the galaxies. So what I'm going to do is give you this deep time sort of scenario for how Missouri began. So the Earth, we have to be on the Earth first, right? So 4.5 billion years ago. So I'm going to use the analogy of that clock here in order to give you some of the history of Missouri. So 4.5 billion years ago, the Earth formed. But if we study rocks, we don't have 4.5 billion year old rocks in Missouri. There's, in fact, no place on Earth that has 4.5 billion year old rocks, except for maybe the interior of the Earth, where some of the first materials accreted into the center of the Earth. Some of that material is probably 4.5 billion years old. But at the Earth's surface, in this outer part out here, the very oldest particle that we know of is only 4.4 billion years old, and that's a zircon crystal in the middle of, Western Australia. And so that zircon dates back to 4.4 billion years old. They use isotopic age analysis to, lead isotopes and uranium lead isotope dating that they use to calculate that age. But in Missouri, the oldest rocks that we have here are roughly 1.5 billion years. So if we take that clock, we're going to have to wind it on past, from wind it down, in other words, from when we get closer to now. So we have to go through 2/3 of geologic time just to get where the oldest rocks are in Missouri. And so I'm going to break it down into 6 episodes here, and here they are. First of all, about 1.5 billion years ago, there were volcanoes in this area. Volcanoes, and then there were later granitic intrusions, and so this was a very stark landscape, but is in fact one in which there would have been life, but we don't have any record of that life here in Missouri. But there were volcanoes back at that time, and later igneous intrusions also in an area that would have been, pretty much in the middle of Laurentia. Laurentia is the name of our ancient North American continent. We didn't really get to become North America until we broke up from a supercontinent that had once formed about 300 million years ago. So in Missouri, we have these volcanoes of Proterozoic time. When we get into the Cambrian time, that's about 1 billion years after that. So 1 billion years later, we had oceans cover this landscape. And then, of course, there were islands. And so these big volcanoes had worn down in that 1 billion years down to almost nothing. And so these islands were around back then. And if you fast forward a little bit, there was stable sedimentation going on in this platform area of Laurentia. And then about 340 million years ago, boom, there was a massive impact, a meteorite impact. And there could have been a couple before that too. So we know of 3 meteorite impacts here in Missouri. And so about 340 million years ago was the Womblow impact, kind of an interesting and important part of geologic history. It was more or less a continuation of what had began during the Cambrian, and so there were shallow seas that covered this landscape, and this meteorite impact struck a shallow sea at a low angle, causing a crater to form, and today the results of that crater are found in around Osceola, Missouri. There's a couple of other ones. There's one south of Steelville, and then there's one north of Lebanon, Missouri. And so those are the 3 impacts that we know of in Missouri. And each one of them has the calling cards associated with meteorite impacts. If you fast forward just a little bit ahead then, so about 300 million years ago, and you can see the clock ticking down in each one of these vignettes here, about 300 million years ago, that's a time when those continents were beginning to come together. And so that massive giant continent that Laurentia combined with Africa, combined with South America. In fact, they called it Gondwana at that time because it also included India, Antarctica, and Australia. And then there were parts of Baltica that had already assimilated and accumulated onto this sort of massive continent. And so everything came together about 300 million years ago, and there were coal swamps that developed, especially in Missouri. In fact, if you go north of Clinton, Missouri, you'll find that there were coal mines in that area. And so this was a time that Kansas City would have been in part covered by coal swamps. And so a very wet, a very lush sort of environment at that time, but it still predates the dinosaurs. But the dinosaurs were here. We know that. There is a dinosaur. There have been dinosaur skeletons discovered in Missouri around Marble Hill south of the St. Francis Mountains. And then at the close of the age of dinosaurs, there was another impact in Missouri about 65.5 million years ago. And this would have been at the end of the Cretaceous time period and the beginning, in fact, of what we call the Paleogene. So they call it the KPG. K is the abbreviation for Cretaceous, and PG stands for Paleogene. And so that's the beginning of this modern era that we live in, the Cenozoic. And so if Missouri had this impact, was there a result from that? What was the result from that? Well, in fact, it was a tsunami deposit. And that's recorded in the Boot Heel of Missouri in Crowley's Ridge. And so if you look in the Boot Heel area, there's one low ridge that runs across. I think Dexter, Missouri is down there. Poplar Bluff is on the west side of a valley that looks out across, and you can see Crowley's Ridge from there. But that is, in fact, the place where there is a record of a tsunami deposit here in Missouri even. Now, if we fast forward just a little bit farther ahead, and we're getting really pretty close to the end of time as we know it, which is today, that is about 1 million years ago, there were ice ages in Missouri. Okay, and so the glaciers came and they deposited all sorts of sediment in the northern part of Missouri, in fact, but the Ozarks, for the most part, were, had a little bit of windblown dust over the landscape, but not as much as they got in the northwestern part of Missouri. And so those were the ice ages. In fact, that's called the Pleistocene. So the Pleistocene is part of this modern time period that we have that it just barely ended about 11,000 years ago. And a lot of people, that's the time when there were mammoths and mastodons and things like that roamed across this landscape, but not dinosaurs, okay? So the dinosaurs had already been long gone at 65.5 million years ago. So let's look ahead. This is the way that geologists look at Missouri. And in fact, if you took off all the soil and you took off all the sediment and so forth, you would be left with a landscape that was nothing but rock. Okay, so bedrock, if you stripped off all the soils and sediments that are in the north, in the part that's covered by glacial deposits north of the Missouri River, this is what it would look like. And so we break it into geologic time periods. And in fact, there are probably 13 of them altogether that are really important to just the average person. Now, if you were to take a course in historical geology, you'd have to learn a lot more than that. But in fact, what we do is we lump everything that happened before the Cambrian and call it Precambrian. And so it was what happened before the Cambrian, and that's when we had the volcanoes and other things here. And that's mostly exposed in the southeastern part of this state in a place called the St. Francis Mountains. So the St. Francis Mountains, in fact, are mostly igneous rocks. They're either volcanic or they're intrusive igneous rocks, and those are the areas that show up in red on this geologic map. The Cambrian areas, when the seas first covered this landscape again, that was during the Cambrian period, and that's the darker orange that you see here. And then after that, those shallow seas continued on and continued on and continued on. And in fact, you get the Ordovician that was deposited after the Cambrian. And after that, there was the Silurian, and then the Devonian, and eventually the Mississippian was deposited. Those are the rocks around the Springfield Plateau. And I think you're going to learn about the Springfield Plateau in this course, but these rocks are the ones that are made out of crinoids for the most part, or carbonate mud, and those are the limestones that cover western Missouri, southwestern Missouri. And if you look at the area around Kansas City, you can see that it's that light green color on this map, and that is in fact the Pennsylvanian age rocks. And so it's a combination of shale, sandstone, and limestone, maybe a little bit of dolomite in there as well. And they find coal, of course, also. So those would have been the coal swamps, and where they had occurred across, and where they're preserved today, anyway, across northwestern Missouri here. And after that, you can see the Cretaceous in the dark green here. So the dark green is, in fact, the age dinosaurs. So there's not much of that preserved in Missouri, as you can see here, but there is some, and that KPG boundary event was recorded in Crowley's Ridge here down where it meets the Cenozoic age sediments. So Cenozoic sediments would overlie that then. And then lastly, there's this sort of floodplain that developed along the Mississippi River and along the Missouri River, and that's in the very light yellow here as well. And so that's a geologic map of Missouri. So geologic maps give us and put a geography on the distribution of rocks in this state. It doesn't mean that, for instance, when we talk about igneous rocks, well, they're underlying everything, okay, in Missouri. Okay, so there's maybe a few metamorphic rocks that may be down, but they're all buried. And so if you can't see them, it's hard to detect them. Well, there are a few deep wells and things like that. So we know a little bit, just a modest amount, about the Precambrian of Missouri and where it's best exposed. That's where geologists know it best, and that's the St. Francis Mountains. So if we go ahead, 1.5 billion years ago, these volcanoes, what were they like? Well, they're referred to as anorogenic. In other words, very commonly when we see volcanoes today, they're usually around the edges of the continents where those continents are interacting with other plates. And so, in fact, there's a tectonic process called subduction where you take one plate and you override it over the top of another plate. And when that other plate becomes subducted like this, that material becomes melted and it forms volcanoes and punches through the Earth's surface. And so here is an image that I've kind of doctored up to make it look Precambrian here, but that's Mount Redoubt in Alaska, and that was an eruption in 1989 here. But if you can imagine, there would have been huge volcanoes in southeastern Missouri at that time. And so not related necessarily to subduction because, in fact, Missouri, that part of Laurentia, had actually rifted apart from other volcanoes. So it's probably closer to a type of volcano that's a lot like in Kenya today. So either Mount Kenya or Mount Kilimanjaro, those are the mountains of the moon. Those are the sort of volcanoes that you would get, in fact, in Missouri at this time, 1.5 billion years ago. Wow, that's a long time ago. Like they always say, what's a few million years to a geologist? It was like, well, yeah, it's not so much, right? 1.5 billion years ago, that was the landscape that we had here. And so these massive eruptions like this would have spread volcanic ash everywhere across this landscape. And when that ash, they say what goes up must come down, and it does, and it forms layers. And so there's up to 400 feet of some of these volcanic ashes in Missouri. They're ancient calderas, in fact, and so these calderas would erupt with massive ferocity and deposit huge amounts of volcanic ash. It's not a sedimentary rock because it's volcanic in origin, so therefore it's an igneous rock. But after those volcanoes had actually spewed their ash and their fragments all over this landscape, it was after that there were igneous rock bodies that began to intrude at depth into those rocks. And today we only see the roots of those volcanoes, the very bottom of those volcanoes. And you can kind of make out from geologic mapping where the calderas actually were. And so those calderas became intruded with igneous rock bodies around their perimeters. And so that is kind of what it would have looked like about 1.5 billion years ago here in Missouri. Would have been a very active place. So the kind of results that we see from this, now this is a photograph that was taken from Prophet Mountain. It's a place where there was a pump storage facility for generating electricity from Amarin Energy. And so this is a rock that cropped out up on that mountain, and this is called the Mountain Rhyolite. And so even as that magma was beginning to crystallize, it erupted and it threw a lot of these fragments of, in this case, a plagioclase feldspar. Those are the white specks in this deep red rock. Now, these are rocks that have a lot of iron in them, and so that's where that deep red comes from. So, in fact, here is a result of one of those volcanoes here. You see these sort of rocks in many places around the world. These happen to be Precambrian, of course, and so it's a very dense rock. And in fact, they use this type of rock along roadbeds, and especially in the St. Francis Mountains because it's so abundant there. And then they also crush it and send it on rail to make the rail beds in many places. And so they call it trap rock in many places as well. So fine crystals of a feldspar there. It's a plagioclase feldspar. And a ground mass that is in fact volcanic ash. Okay, so the volcanic ash is so old and so compact and was so hot when it formed that the crystals all melted together. You can't see them, okay, but they're there. When you look at them in thin section, you can see tiny crystals, but the boundaries are a little bit fuzzy. So that's the Monger Mountain Rhyolite. There were other sorts of interesting byproducts of these volcanoes when they erupted as well. If you go to a place called Johnson Shutins, you'll see volcanic rocks in the shut-ins themselves. And this is the aspect that you see at the very bottom in this image here, where that stream has cut through that shut-in area where very dense rock is very difficult to erode. And in fact, if you have a boulder, sometimes it'll drill a hole in some of these rocks and it makes these sort of pothole sort of shapes. And so the rapids that go through Johnson shut-ins look a lot like that is them right there. And so, but it's a dense rock like that. It was kind of a dam, if you will, that the river had to cut through in order to have a big wide valley upstream and then downstream. It goes through this narrow gorge and it erodes away those rocks very, very, very slowly. But if you go downstream from the shut-ins themselves, you'll go to see places like these upper two rocks here. So the one on the left-hand side, those are little round pellets, okay, of volcanic ash that would have formed up in some of those clouds. And so as you probably know, volcanoes generate their own weather. You've probably seen some striking images of lightning and things like that from some of the eruptions, maybe in Iceland and a few other places around the world today. But in the ancient past here in Missouri, these things would actually have had so much static electricity in them that the particles began to stick together. These things are called lithophysi, and I don't think that's going to be an important term to you, but it is to geologists. And we have these little tiny rock hailstones that would have fallen from the sky and accumulated on the ground surface at that time. And so this is what they call an ashfall tuff here. But it's one in which those particles stuck together and became accreted in the atmosphere, in the early atmosphere. The one on the right-hand side is also interesting because there were still streams and all back at that time. Well, if you've got static electricity and lightning and you have volcanoes, you're going to have rain as well. If the rain falls on this landscape, okay, it's already hailed on us, right? So the rain falls, there's this volcanic ash that's laying around. The streams come by, and then you can actually see ripples in some of this. So this is actually a water-lain tuff right here. Now, it's not a sedimentary rock. It's still an igneous rock because it has a volcanic origin, which doesn't seem to make a lot of sense to us. But, you know, to sedimentologists, it doesn't make a lot of sense. But you can actually see ripples. Now, use a knife as a scale for those two rocks in the upper part here. But you can see the ripple that's just below that knife there. And so that's a surface that would have been washed by water and removed some of the volcanic ash in a stream. And so that is a water-lain tuff. So those are the kind of rocks you expect to find around volcanoes. Other places in the Ozarks are really pretty spectacular. And after you have these volcanoes erupt, the igneous rocks in that magma chamber that was down below that volcano continued to make its way upward, and it ate into some of those volcanic rocks. That's how they tend to work. And so it works a lot like a lava lamp as well. So the lava blobs would come up. Not really lava so much. We call it magma. That's the molten material that eventually is going to become rock. It's either going to explode as a volcano or it's going to become an intrusive rock, like the rocks you see here. Now, this is a granite right here. This is a granite that's exposed at Elephant Rocks. So Elephant Rocks is a spectacular sort of place. And so Elephant Rocks are erosional remnants of the weathering of that granite. So this is a place where they quarried granite for a long period of time. But in fact, those elephants they left behind because they were so strikingly beautiful. There's a lot of aesthetics in geology as well. And so that igneous rock had weathered along fractures. You can see some of the fractures in this big elephant right here. Now, they're not really elephants, right? But you see that it's a big erosional remnant. And so the fracture would have been parallel with the top surface below, and it's eaten out below that. And then there would have been fractures on either side of that elephant as well that became etched out, and the sediments and soils washed away eventually. And so here you can see on the right-hand side some more of these blocks that have tumbled down the slope here at Elephant Rocks. And you can also see where the water is accumulating. So very, very slowly this landscape is being eroded by standing water in pools and pockets like that. So what would it have looked like back then? Well, I try to imagine this, because we have to have a pretty good imagination to try to put yourself in the time machine that takes you back to 1.5 billion years ago. So what was it like? And so we know there was a rift zone off the south end of Missouri. When something ripped it apart, it was actually a piece of South America now. But those volcanoes were here. And so this is like one side of the East Africa Rift Zone. And you can see what I've done here is I've taken an image of one of the calderas from Bali, and I've superimposed that on this landscape that would have been rich with iron and dust and volcanic ash, and you put the volcanoes in the middle of that. And so it looks a little bit like that on the upper part up here. I've tried to put in the outline of Missouri here to indicate what it would have looked like as well. So that's the very beginning. That's the basis for what is happening in Missouri. A little over 500 million years ago. 520 is what I put on this, but it's very indefinite. The beginning of the Cambrian started about 542 million years ago, and it ended roughly about 488 million years ago. So there's a span of about 30 million years that was Cambrian. So I kind of split the difference there. I made it 520, if you will. Most of the rocks in Missouri that are Cambrian in age are late Cambrian in age. There's a few that are middle Cambrian in age as well. But what would that landscape have looked like? Well, some of those volcanoes, if they're still weathering today, they would have weathered even back during the Cambrian. And so here's your Cambrian landscape, if you will, with pockets and islands of volcanic rock sticking up, and the seas rose up and began to encroach across this landscape. Well, the reason they did that was because not only was there a rift that began after that, there was a supercontinent that broke up all over the world, in fact. And so not only did something rift apart from the south edge of Laurentia, there was rifting going on everywhere of a supercontinent that was called Rodinia. So as Rodinia rifted apart, sea level rose, and it rose around the entire world at this time. So the base of the Cambrian, about 542 million years ago, saw this huge rise of sea level because of that rifting and the break apart of that supercontinent. So here you can see an image. This is one that I took from, I think it was Thailand actually, but I've put on a few blocks like elephant rocks here on the top of one of those little pinnacles, if you will, and put some other islands out here. So this is kind of a painting with Photoshop here, but that's what it would have looked like perhaps during Cambrian time. Around these igneous knobs, there would have been sands that were deposited, in fact, in Missouri. That's called the Lamont sandstone. It's very rich with volcanic material, and still it's got a lot of quartz in it. It has a lot of feldspars in it. It's what we call a feldspathic sandstone. And so after that, as sea began to rise even more and more, then because we were at equatorial latitudes, you began to accumulate carbonate rocks. And so the carbonate rocks were deposited over the tops of many of these islands. And we see a result of that here in that top image. This, again, is near that Ameren energy production area where they use hydroelectric energy to have that pump storage unit. And this is where it would have come out. Okay, so this was after that 2004, 2005 flood. Or excuse me, just before that. But here you can see the igneous rocks, and you can see that surface. And in geology, we call that a nonconformity, where you have igneous rocks that are overlain by sedimentary rocks. So the rocks on the far left-hand side of the top image here, those are mostly dolomite, maybe a little bit of limestone in there as well. And some of it's a little bit shaly too. So there's a mixture of different kinds of rock in there. But those rocks actually lapped up onto the craton or that island at the time, and in fact they became very finely compacted off to the left-hand side here. So originally they would have been deposited more or less horizontally, but they could have lapped onto that surface here. And so that is a nonconformity, and there's roughly 900 million years of time missing there. So the age of the base of the Bonne Terre Formation here, and then the igneous rocks of that sort of volcanic events that happened during the Precambrian here. 900 million years is a long time. Even to a geologist, that's a long time. If you go a little bit farther, there's Dr. Rovey, and you can see him with some other students here. I was on a field trip with them back in the summer of 2004, 2005 here. This is a place called Park Hills, Missouri. And this is the Davis Formation. So if you take that basal carbonate, okay, that was deposited in shallow seas around the Ozarks, sea level kept rising and kept rising. And in fact, over the top of the students and Dr. Rovey here, you can see a layer of what we call stromatolites. Stromatolites are a living organism. It's the first living organisms we really kind of see, other than maybe a handful of trilobites in the Bonne Terre Formation. These stromatolites were pervasive, and in fact, they still live today in places like the Great Bahama Bank, and you can also see them in Shark Bay in Western Australia, and that's what you're looking at over here on the right-hand side here at the very bottom. That's our modern analog for what it would have looked like back during the time when those rocks were deposited, 6-8 feet above Dr. Rovey there. So it would have been high water back then. If you zoom in a little bit closer in time, or we look at time now. So the next part was there were carbonates that kept accumulating on this very stable sort of platform, and they kept accumulating for a long period of time, until eventually there was an uplift, and that uplift probably occurred during the Devonian. The best estimate that we have for it, that it was a Middle Devonian uplift. And so it's a time, in fact, when Laurentia, if it was drifting loose from the rest of the continents, it eventually began to have another microcontinent impinging from the south. I have to remember, most of Arkansas didn't exist back then. Only the very southern part of Arkansas, the very northern part of Arkansas were around at all. But as a microcontinent began to drift north and impinge on Laurentia at this time, it would have downwarped that part of the crust and overrode it slightly, and then it would have popped up in the Ozarks, and that's the beginning of the Ozark uplift, Middle Devonian time. Most of the rocks that predate the late Devonian have been truncated, especially in Arkansas and in northern Missouri. Actually, if you go around Fulton and areas like that, you'll actually see little pieces of upper Devonian rock exposed in some of the rocks, some of the road cuts and some of the quarries that are in that area. And so the Devonian was blanketing this area. By late Devonian time, it had blanketed this area, and then uplift was continuing, of course, right, as this southern microcontinent began. We call it the Ouachita Lochthon. It was impinging on Laurentia, and it warped this area up, and next thing you know is you have another unconformity developed, and that was at the base of the Mississippian. So the Mississippian began to cover much of the Ozarks at this time. We just don't see it preserved in many places. We do in the Springfield Plateau, however. So the Springfield Plateau has this cap rock of Mississippian age rocks, and those are about 340 million years ago. 370 million years ago, you uplift it, and then you deposit some rocks, and then most of those were washed away prior to about 340 million years ago when the Mississippian was deposited. So as the Mississippian encroached upon this, we had an area that was underwater again. And so as it was underwater, crinoids would have lived in this area. They would have made huge tracks of carbonates that would have looked a lot like the Bahamas, in fact. In fact, throughout much of geologic time, this central part of the United States was mostly underwater. It wasn't until Devonian time that you began to form the earliest phases of the Appalachians. Okay, the Appalachians began to rise up in late Ordovician time and then into Devonian time, and then eventually got back over here on the west side and began to upwarp these areas. And so you deposit over the top, in this case, of eroded lower Ordovician age rocks, you deposit Mississippian age rocks over the top of that. And so what you see here are crinoids. Crinoids are referred to as sea lilies. They're a type of fossil that makes these little tiny round disc shapes. And in fact, they have little cups at the top. So it's a little bit like a starfish at the end of a stalk. And these things would have stuck up into the water column and filter fed on protozoa, microbacteria, things like that, and would have made their living doing that. They were rooted on the seafloor, and they lived in this land, in this sort of like flat, watery landscape that was a lot like Great Bahama Bank. They lived and died, their pieces fell apart, and you see things like this rock on the left-hand side here, which is a crinoid grainstone, we call it in the geology business here. But that shelf that formed this area in Springfield would have been a shallow sea at this time. That was deep water out in southern Arkansas as that microcontinent was approaching. But onto that landscape about 335 million years ago, just after the Mississippian had begun to deposit rocks in this area, there was a visitor from outer space, and that visitor from outer space, kabam, hits Missouri around Osceola, and in fact, this is an artist rendition right here of what it would have perhaps looked like. That's Don Davis, and that's actually from the KPG boundary that he did a painting here. But you can see where a meteorite struck in Missouri, and this is an image of what it would have looked like at that time. And so there's two parts to this image, in fact. There's about a 400-meter impactor that came in. Okay, how 400 meters? Roughly the size of Busch Stadium coming in and colliding with the Earth, right? Kaboom, it hits, and in an area we call the main impact area here. It's where the town of Vista is at the northern perimeter of this, and so you can see the smaller circle within the larger circle here. It came out of the southwest. Well, back then it was actually the west, but North America has rotated since then. And there's a larger circle that outlines what we call the tectonic rim, okay, for that impact here. So if it hit in the southwest down here, it caused devastation all the way around, up to 19 miles across that larger sort of tectonic rim here, but only about 19 kilometers, 12 miles across. And then for the smaller main impact area, that was 8 kilometers across, or 5 miles across, if you will. So it's in between Collins and Osceola. If you ever drive up Highway 13, you drive right through this thing. And you see some of the rocks on the sides, right? So on the road cuts, you can actually see some of that impact breccia here. And so the impact breccia in this case is really pretty amazing. And so when you dissolve pieces of that, you get little clues as to the origin of this structure. So here we are looking at that main impact area again. This is the ground zero for that impact. And Highway 13, in fact, cuts right across the eastern side of this. But there is a quarry just about 1.5 miles outside of that main impact area. And this shows you some of the devastation that would have occurred in this area at that time. There's a block of what we call the Northview Shale up here, their Northview Formation up in the upper part up here. That's Dr. Jim Miller down here at the bottom. And so that block would have been flowing outward and being washed away from that impact. Okay, so it was a marine impact during the middle of the Mississippian time. Kaboom, it hits, and it causes devastation all in this area. We get all sorts of rocks called breccias. And so one of the breccias that we get here, on the left-hand side, you can see Dr. Rovey standing on a block there, but in between the two big blocks over here on that quarry face, you can actually see an injection breccia where it just wedged in and forced those two rocks apart. So really quite a lot of devastation in this place. It took and it folded rocks as well, and so you get these isoclinal folds and you get thrust faults and things like that. The sort of devastation that you would expect to see deep in the mountains as mountains are forming, that's the sort of processes that were occurring in an instant when this thing hit. And so that's me next to the quarry wall here. I didn't want anybody else to be that close to the danger here. But there's a thrust fault right at my head level there, and you can see the fold that's up above that here. So amazing amounts of pressure on these impacts. It takes these rocks, and when it breaks them, it turns them into a rock we call breccia. And here you can see the matrix on the right-hand side from that quarry, where it just took and it exploded that rock in place, and all the material around it flowed in around to form the matrix in this case. And so that is a breccia here. That we call it a dilation breccia because the rock is just essentially larger because it was in a low pressure zone and the rock just exploded. So when we make cartoons, we try to convey information. So there would have been an impact. You're 1.5 miles outside of that. You fold the rocks, you bend the rocks, you thrust fault the rocks. And so you fault them a lot of different ways, in fact. But there's a surface at the bottom where all of this material would have ridden out. and there would have been blocks plucked from that surface and incorporated into this breccia. Well, we call that a mega breccia when the blocks are really big enough, like the giant blocks in that quarry wall, or some of the smaller blocks like were above Dr. Miller there. That was a piece of a mega breccia right there. But they get smaller and smaller as you go up in this thing, and so the breccias become more and more fine-grained upwards. And there's indicators in there that this was a water-lain breccia at the very top surface of that. And when we take that top breccia and we dissolve those rocks, what we find is there are, in quartz, in little tiny quartz grains, there are indicators of really enormous amounts of pressure. We call it shock pressure, in fact. So when you take and you apply enough pressure to quartz, it doesn't always break in scallops. We call that conchoidal fracture to our Geology 110 students. But in fact, when you have enough pressure on quartz, it actually goes along those crystal lattice faces, essentially, and it aligns these things up. And these things are called planar deformational features here. So those PDFs are planar microstructures that are lined up here on a roughly a 10 micron sort of scale. Those things indicate exposure to shock pressure. And that's one of the diagnostic things from meteorite impact. So you have to have good evidence for any sort of argument that you have. And so this is work that was done by Dr. Rovey, did some of the work here. And then also Jared Morrow from San Diego State University worked on some of this as well. Here you see that same digital elevation model at the bottom down here. But you can see that there is a sort of trajectory that went from the southwest, that's the lower left-hand corner here, up to the northeast, which is in the upper right-hand corner here. And so that is the story of the Wablo impact structure. So if you know that you have an impact structure and you're looking for this evidence, what do? Well, I mentioned it to one of my good friends who works for MoDOT, and MoDOT came out and drilled several cores from this impact structure. And you can see one of the cores over here on the right-hand side, where it shows that sort of devastation and the sort of breakage that you get from these rocks. Now that was drilled all the way down to 300 feet, and it keeps going. So the breccias here, we've never hit the bottom of the breccia. So it'll be interesting to see what happened. Likely, after this impact occurred, there were probably islands around the perimeter where the crater rim should have been at that time. And so it's a very interesting sort of story. It's a narrative, really, because science isn't about storytelling. It's about gathering evidence, but then presenting it in a coherent fashion where we can kind of turn it into, this is what we think happened here, okay? So if you have evidence contrary to this, you need to disprove this, okay? But all of the evidence that we have right now points toward an impact, and not a volcanic eruption, in fact. And so here is the cartoon version of what would have happened. There would have been a low-angle impact to hit shallow seas. It would have carved out a crater. It exploded when it detonated, essentially, and it would have made a breccia lens, and so it would have forced out water from this area as well. And we have evidence for tsunamis that would have been generated, in this case, by an impact, not by an earthquake. And so this is the resurge breccia that flowed back in. That's some of the yellow breccias that filled in up to the top of the crater here. And then there would have been shallow seas that covered this up again at one point. We don't see a lot of those rocks preserved, but in fact what we have are some of the chert clasts that are not broken to pieces like that breccia. And those chert clasts, in fact, have yielded some fossils that would indicate that it's the next age in the Mississippian. So it would have been covered by seas once again after that impact. And then after that, of course, there were the Pennsylvanian age rocks, and we're going to talk about that in just a second here. So if we look at the three impacts in Missouri, ironically, they all line up. There's the Wablo impact over here in southeastern St. Clair County. Here's the Decaturville impact. It's right on the border between Laclede County and Camden County. And so it's a little bit south of Camdenton. It's a little bit north of Decaturville. It looks like a little donut over here. Well, if you take the match line for the east side of that digital elevation model here, and you match it over here on the left-hand side of the bottom, if you keep going to the east, there's Crooked Creek structure, and that's in Crawford County in southeastern Missouri. They're separated by about 200 kilometers along here, and it may be easy to say, it's like, wow, there's three impacts and they're all in a row? Doesn't that mean it was a serial impact? Kind of like the one that hit Jupiter back in 1994? And so there was a serial impact that hit Jupiter. It was the Shoemaker-Levy 9 comet that struck it. And in fact, that was proposed for this area as well, for about 9 structures that line across here. There are like 9 different areas, but in fact, only 3 of them have the diagnostic evidence that suggests that they were meteorite impacts. And the irony is that no, they're not the same age, in fact. And so Woblo hit at a different angle from the other 2. We don't have really good evidence for how the other 2 hit, but they're not lined up. They're not in a series along that same line, 200 kilometers long. It can't work, therefore. So we've disproven that hypothesis by having a directionality and a trajectory that we can document with the Woblo impact structure. That's our argument, in fact, for saying that this was not a serial impact. Okay, we're going to fast forward a little bit now, so I've hopefully dispelled any ideas that there is a serial impact in Missouri, but that has yet to be written, so that's for this summer, right? So in Missouri, we're going to have the clock tick down a little bit more, and we're going to look at some coal swamps. And these are the sort of rocks that are exposed around Kansas City, a little bit north of Osceola. Remember those light green rocks that we saw? Well, here is a digital elevation model for the entirety of the Ozarks right here. And if you look at it, there's really a few parts to this area. So you know about the Springfield Plateau. That's kind of in the light green area in this digital elevation model here. And the St. Francis Mountains, well, those are over on the far right-hand side over here, and just a few knobs that stick up really, really high. And in fact, the Mississippian on the Springfield Plateau is a really high area too. And so that is indicated here by the little brown spot that's out around Cedar Gap. So Cedar Gap is enormously high. It's about 1,700 feet high. For the Ozarks, that's pretty high in Missouri. But if you cross the White River drainage, that's the large dendritic drainage area that came out of the middle of the Ozarks here, flows out to the Mississippi River down here on the right-hand side. If you look in Arkansas, those are the Boston Mountains. And so the Boston Mountains are the highest mountains in the Ozarks, in fact, and they've been uplifted significantly by that same event. But during Pennsylvania time, it was the culmination of the docking of this Ouachita Lochthon at that time, and there would have been a huge amount of sediment that was deposited here. And in fact, it's during a time period we call the Atokan during the Pennsylvanian. And during the Atokan, in fact, that's when much of the Arkoma Basin had subsided very, very deeply. And there's a huge pile of sand that was deposited in the Arkoma Basin and also in the Boston Mountains here. In the Boston Mountains, those are the high Ozarks down here. And those are the ones you see down south of Fayetteville and a little bit north of Clarksville and that sort of area, north of Little Rock, in fact. So that is a snapshot of what the Ozarks look like here. I like to tell people it looks a little bit like a pork chop, okay, with the bone being down here at the bottom where the Boston Mountains are, in fact. And so we're in the meat and the fat part of here in the Ozarks. But if you get beyond the pork chop here to the north, that's the Osage River drainage here, the Osage and Mer de Seine River drainages. And so they are what carve up the north side and kind of define the north side of the Ozarks here. And in fact, if you go a little bit farther north of that, you can actually see the Arkansas, the Kansas River, where it empties into the Missouri River, and that's Kansas City right up there. Those two rivers that come together in the northeastern corner of this map. So that's the Ozarks. Most of this area to the north of the Ozarks was deposited over the top. There was sandstone and shale and a little bit of limestone eventually when seas encroached into this landscape as well. Now, interestingly enough, in places in southwest Missouri, we still get some of these Pennsylvanian age rocks. It's not just exclusively in the Boston Mountains. There was so much sediment, in fact, that many of the rivers drained to the north in order to go across this landscape, and they cut valleys in the limestones that covered much of the southwestern part of Missouri. And so those channels, in fact, cut into the limestone, and there's roughly about 10 million years of missing time in this area, 10 to 15. And so when you look at some of the areas in Missouri, you know that, well, this is the cave state, right? But not all of the caves are open anymore. Some of them were closed due to COVID and a few other reasons, right? But in fact, you could have developed caves just as soon as you took those limestones up above sea level again when they were raised up with this Ozark. The culmination of that Ozark uplift happened after Mississippian time. And during that culmination, of course, you would form caves. And so what you see on the right-hand side here, that is a shale-filled cave that's full of Pennsylvanian age rocks, and that cave cuts into Mississippian age rocks. So this would have been very near the land surface, in fact, and it would have carved that cave out and then deposited some of the Pennsylvanian sort of sediments into that cave. And so that's at South Greenfield here in Missouri. We find fern fossils and things like that. So that's a fern fossil from up at the Wablo impact structure from some of the Pennsylvanian age rocks that blanketed over the top of that impact structure. So that's I forget the name of the fern, but it's one of those sort of ferns. And if you are in South Greenfield, you would also see not just shale filling these things, but also some sandstone that has cross-bedding in it. It indicates that we're currents that were flowing through it. They're not ocean currents, in fact. They're fluvial deposits. So rivers would have been flowing through some of these caves or into this landscape, if you will. So there's older rocks in some of this area that have been karstified, and then there were sands and shales that were deposited. And so here you can see some of those cave fillings. And so we call this it's a sandstone-filled cave, in fact, is our interpretation for this. Roughly about 10 million years missing. This is an irony here, right? So the irony is that the older rocks are at the top and the younger rocks are down below because they're filling in a cave. So that kind of violates one of the principles of geology, in fact. We call it superposition, where older rocks tend to be at the bottom and overlain by younger rocks successively. And caves violate that. It's really kind of an interesting sort of observation. So if we have a lush landscape that's full of coal swamps and we're having rivers that flow through this landscape as well, you can actually see that these coal swamps, in fact, deposited a huge amount of sediment up north of Clinton, Missouri. You can see some of the strip mines across these linear features that you see in this aerial photograph here, Google Earth capture, I think it is. And in fact, those linear sort of features would have mined out about a 2-foot thick seam of coal there, 2 to 3 foot thick. And sea level, after these coal swamps had been deposited, compressed plant debris, and coal would have been a result of the huge forests that covered this landscape at that time. And that gives you a snapshot of what the forests were. They're not the same kind of forests that we have today. Most of the trees that we have today didn't even evolve until after the Cretaceous extinction event. But these would have been some of the early trees, gymnosperms and tree ferns and things like that would have lived back during Pennsylvanian age time, about 300 million years ago. And so those coals developed from these plants living and dying and then becoming sequestered, and their carbon being sequestered in those swamps. And then they got buried by more Pennsylvanian age rocks. And so the Pennsylvanian comes along and buries this sort of landscape. We had mined the coal here in the Tebow coal mine area for the Tebow field, in fact, all the way into the 1970s. But they stopped mining the coal because we have a very high sulfur coal here, and it leads to a lot of pollutants. And of course, the Clean Air Act of the early 1970s resulted in people wanting to burn a much, much cleaner coal, which would be low in sulfur content. And so today, in fact, when we burn coal, most of the time we burn natural gas, but sometimes we burn coal for our energy needs here in Springfield. That coal comes from Gillette, Wyoming, in a place called the Powder River Basin. So those coals are mined in really thick seams, like 15 or 20 foot thick seams of coal there. They're loaded on trains, and the coal trains run across all of the Midwest in order to deposit that coal here at our power generating facility in the Southwest Power Plant here. So that is essentially 2/3 of our way through this geologic time scale. We're going to go pretty quick through the next one here. Remember, this is a time after the Pennsylvanian. There was a massive extinction that occurred at the end of the Permian. So the Permian rocks in Missouri, they were probably deposited here, but they were removed by erosion probably. And so those rocks are actually, they crop out in around Topeka, Kansas. And so they would have come into this area and been deposited here, but they're no longer here because of the uplift that we had with the Ozarks. And so, in fact, those have been removed by erosion, but they are preserved in central Kansas. So with the Permian extinctions, when they occurred, massive outpourings of lava, again, a volcanic story, it would have changed the climate, and we went from this lush coal swamp sort of setting into deserts essentially. And it's roughly the same time that all of the continents came together and we formed this massive supercontinent called Pangaea. So Pangaea came together with when we had Gondwana come together. And Gondwana is Africa, South America, Australia, Antarctica, India. All of those continents were together in Gondwana. And then Gondwana and Laurentia came together roughly around 300 million years ago. And that's when the Appalachians really went through a massive phase of uplift. And then, of course, the Ouachitas came in after that, and that was during Pennsylvanian time, during the Atokan. And then there was devastation and pretty much mountain building all the way into Texas and into Mexico, in fact, at that time. And then there were uplifts popping up in the western part of North America as well. So we formed this massive continent called Pangaea. We went into desert conditions, and the next thing you know, we had dinosaurs that developed during the Triassic. It's a time when there would have been very arid in this landscape, but these dinosaurs developed and they wandered across this landscape as well during the Triassic. By Jurassic time, things changed again. And so we had massive volcanoes erupting in the western part of North America during the Jurassic, and we had wet conditions again. But we didn't have the Rocky Mountains at that time. The Rocky Mountains had been built during Pennsylvania time and eroded away really, really rapidly in something we call the ancestral Rocky uplift. So, boom, boom, the little mountain range developed and it dropped back down and it was covered by seas. And so, in fact, during much of the what we call the Mesozoic era, that's the Triassic, the Jurassic, and the Cretaceous, much of that time period, in fact, there were shallow seas that stretched all the way from the Gulf of Mexico, which began during Triassic time, and those seas stretched all the way to the Arctic Circle. And so they call that the Western Interior Seaways. There's a great book written about this called The Seas of Kansas. And so, in fact, they find a lot of swimming reptiles in those deposits. And there was this huge push to try to collect who's going to collect the most fossils. And so they had what they called the dinosaur wars at that time as well between Cope and Marsh, the famous paleontologists. And so these seas came in. And then they went away again because there was subduction going on the West Coast. We developed the Sierra Nevada mountains at that time, the precursors to the Sierra Nevadas. You got a rain shadow effect. And again, there were swamps across much of western North America. It's a time, in fact, when dinosaurs roamed this landscape. And it's the Morrison Formation, one of the most famous fossil-bearing dinosaur beds that you can find anywhere in the world. In fact, there's maybe a few places like in Mongolia and China where you see the same sorts of beds during the Mesozoic. But here we have the Missouri at the end of the Mesozoic era. So at the end of the Mesozoic, boom, from outer space, there came this sort of like visitor again. It hit the Yucatan Peninsula. So if you look at the Yucatan Peninsula as a little bit, well, I like to draw, okay, if this is Mexico right here, the Yucatan Peninsula is that thumb that sticks out here. So on the tip of that thumb, you would have had an impact there that was not 400 meters across. It was 12 kilometers across. So if you can imagine a globe and having a little tiny grain of sand, that grain of sand struck the Earth and it changed everything on this planet. It caused the extinction of dinosaurs, causing a change in the climate. It sent deposits and caused forest fires around the world because when it hit, it blew material into outer space, and that material came back down, got superheated when it ran through the atmosphere again. The reentry of those hot particles sparked forest fires around the world. There's a soot layer that would have gone along with that as well. They claim that the oxygen content of the atmosphere was roughly around 30% at that time. It's as though you could almost have spontaneous combustion going on. And the dinosaurs were able to live because of that, but they weren't able to live after this impact because of the climate change, or they may have been too close to the impact itself, because that generated some things like the tsunami that hit in an area that was called the Mississippi River embayment. And so if there is an extension that goes from the Gulf of Mexico all the way to the Arctic Ocean in the western part of Kansas and eastern part of Colorado, that was called the Western Interior Seaway. Well, this is another area that was shallow ocean water at that time. During Cretaceous time, there were crocodiles that had been preserved in parts of southeastern Missouri. That impact here in Chicxulub sent tsunamis into Missouri, and it caused the sort of devastation that you see in this photograph, which is a trench that was cut into Crowley's Ridge, and it shows you, I think it's called the Owl Creek limestone, but it's the Owl Creek Formation, but there's a tsunami in there that has a lot of fossil debris. It has a lot of shelly material. Yeah, the Owl Creek is down below here. And there's a glauconitic layer above that and then a gray layer above that. Well, that impact itself is represented in this case, again, by a breccia, if you will. They call it a coquina here because there's so much shelly material in it. But that's the tsunami deposit, in fact, there. So this is not my work. In fact, this is the work of Carl Campbell, who is at St. Louis Community College in the St. Louis Community System. And then Franca Obo-Ikenobi, who is at Missouri S&T. And so she studies little tiny microfossils in that deposit. And Carl Campbell knew about this sort of place in Crowley's Ridge here that left these tsunami deposits behind. Fascinating history to Missouri and our impacts. Those are not the only three impacts. This is another one that was a result of an impact in Mexico. So a long ways away. So here's just one more image of that sort of area, and you can kind of see the stratigraphy here that's on the right-hand side. That's a stratigraphic column, and the tsunami deposit roughly at the very bottom down here of this rock unit called the Clayton Formation. So the Clayton Formation would have been the Paleogene sort of rock, and the rocks below that, in fact, would belong to the Cretaceous system. So that's the KPG boundary in Missouri. You didn't know that we had that here, but in fact, the KPG boundary was found in Italy first. It was found in Gubbio, where they found iridium concentration in a layer of clay there. And so it's really an interesting sort of time period. And so the animals that were in Missouri, we find a mosasaur. It's actually a reptile that was deposited in probably a sink fill around Marble Hill in Missouri. And so that's a mosasaur on the lower right here. So if that's the case, have we had other sorts of things? Well, if you're familiar with the boot heel of Missouri, you probably also know about the New Madrid fault zone there. Now, I'm only giving you this because there have been other time periods when there were things like tsunamis that occurred in southeastern Missouri due to impacts, not the impacts in this case, due to earthquakes. And so there's the famous 1811, 1812 earthquakes that occurred. In a swarm of earthquakes, in fact, over the next few years, that these were like magnitude 7.4 up to like almost 8, magnitude 8. These were earthquakes that occurred when the earliest European settlers came to this landscape, and so they built little tiny log cabins, things like, well, this is the event that shook those log cabins down. It created a lake that was 100 miles long at Railfoot Lake. It caused the sunk lands to occur and the north side of Crowley's Ridge. So it just subsided very, very rapidly in these places. And there were sand volcanoes that erupted. Sand that became so liquefied that it shot out of cracks in the earth developed from that earthquake rupture that had occurred at that time. The story is, the narrative is here, it's not a story, because stories are usually fictitious, and this is a narrative that was written by eyewitnesses that the Mississippi River flowed backwards at this time in 1811, 1812. There were river barges and things like that were riding giant surges of water across the landscape. And in fact, these are not tsunamis in this case. These would have been what they call seiches. Seiches are more like sloshing of water. Although the Mississippi River running backwards was due to probably a block uplift, a minor amount of block uplift, but it caused the Mississippi River to flow backwards for a short period of time. So that's what you see in this woodcut over here on the right-hand side is some of the water devastation for places around New Madrid and all along the Mississippi River Valley here, south of where the Ohio and the Mississippi come together here. And in fact, those earthquakes were felt all the way into southern Indiana, in fact. So we live in a very active seismic area right here, I guess I would say, from a modern standpoint. And but we're going to still backtrack a little bit here, okay, to go back in geologic time still a little bit more. But I just wanted to show you that there are other things that can cause deposits like that. But in fact, those right at the KPG boundary must have been from a tsunami. So we're going to go to the last vignette. So the last vignette is all about the ice ages, and it's really all about the Pleistocene. And so the Pleistocene was the last ice age. It went from about 1.6 billion years, well, 2.6 billion, geologists I get screwed up with this. The older I get, the more like billions and millions like tend not to make too much sense to me, but at the same time, very important terms. Less than 3 million years ago, okay, so, and in fact, what we're talking about is 2.6 million years ago to about 10,000 to 11,000 years ago. That was the Pleistocene, and there were glaciers that covered much of North America at this time. And in fact, you can see on this image right here where the glaciers extended into northern Missouri, and you can see the outline of where the glacial edge was at that time. Some of the rocks that we have in this area are not rocks at all. They're still sediment, in fact, and it's a product called loess, Loess, or if I were to give it the correct German pronunciation, it would be Lurs. But O and E is kern letter, right? And so Lurs is this windblown silt that would have been right at the front edge of that glacier. And so this is the kind of the last time period that was of any consequence in Missouri, other than the time period that you live in, of course. And so this is when we had continental glaciers that covered the landscape in the wintertime. There would have been massive sand dunes or dust dunes at that time. And so if you ever go up to northwestern Missouri, you're going to see the Loess Bluffs, they call that area. Very steep hills. And loess is interesting because you can cut a vertical cut in it, and it won't slump unless you cut it too shallow. If you cut it vertically, it'll hold together, and it looks like dripping wax along that surface. Well, cliff swallows love it. Bumblebees love to make their nests in it. But it's a very interesting sort of place. But it also records one of the last vestiges of the megafauna. Now, the megafauna pretty much died out about 5,500 years ago, and that would have been in the Arctic North. And Wrangel Island had they still had massive, woolly mammoths at that time, dwarf woolly mammoths, mind you, but small proboscideans, right, the elephants, right, that would have lived in the Arctic North at that time. They went extinct about 5,400 years ago, but they roamed across the landscape of Missouri as well, 10,000, 11,000, up to 20,000 years ago. These things were, and all over this last time period. So elephants were common here. North America is the home for camels. It's the home for horses, for that matter. That's where much of the early evolution of horses and camels occurred. But then they spread across that land bridge and went into Asia, in fact. But the mammoths never made it away from this area, the ones that were North American ones anyway. And so they find, in fact, well, we don't know what caused the extinctions, but some people think that humans hunted them for meat, for hides, for all the products that they would give us, in fact. But that remains to be seen, because as it turns out, there's another hypothesis. And so that other hypothesis is that there was an impact onto that ice sheet, and that if it hit that ice sheet, it could have blasted material out. And ironically, they actually find little tiny pieces of micrometeorites in the tusks of some of, and one or two anyway, of the mammoths. And so, yeah, the story of science has not been entirely written. Okay, the narrative of science definitely has not been completely written yet. And so there are things to learn and to know, more things than you can possibly imagine. And so, I hope I've given you just a little bit of insight into the origin of the earliest rocks in the Ozarks in Missouri, and then what's some of the things that transpired, how the seas came in afterwards, and massive volcanic eruptions. And then we also had, meteorite impacts. We had 3 of them, in fact, in Missouri. We've had these time periods where there were coal swamps that deposited rocks in Missouri. And we've mined that material and turned it into a resource and were able to use that. But we've also had these climate changes as well. And so if you look for a ground zero for climate change, Missouri's kind of it. We had massive ice ages that extended all the way down into Missouri. And then when you melt those glaciers, it doesn't affect Missouri so much, other than we have all of these materials left behind like loess. But in fact, climate change is going to affect us as well. And it already has affected us. Many of folks would argue, and I think Dr. Pavlovsky would agree with me in that. Anyway, that's the story of Missouri, in fact, and so that is what you get as an introduction to the geology of Missouri. I hope this has been helpful for you, and I'll post this up to YouTube, and you'll get to see it either in class or at your leisure at some point. But anyway, thanks a lot for listening to Written in the Rocks, and I'll talk to you soon. Thanks. Bye now.